All right, so let's do a little different statically indeterminate problem here. This is got two redundancies. This is problem 440. So what we have here is a rigid bar here, beam, okay? And it's supported by these three rods. Now on the lower rod, basically what you have is a detail where you have a turnbuckle. So the way it works is actually, you know, if I were to try to blow it out a little bit, here's point E, comes through the element and then goes down. So here's that rigid bar. This is point E. And it comes down to a section here where there's usually a thread on one end, and then actually we have a thread on a lower segment that then goes down and is pinned at point F. So these are actually split. And then we have a turnbuckle here, which if you've seen those things, I don't know if I'll be able to draw it nice. They're kind of like a hollow tube with a mating thread. So as I turn it, let's make a look at a cross section. This is actually the turnbuckle. It connects these two rods. Okay? As you turn this, it's going to pull these together or pull them apart depending on where you turn it, okay? So this problem says we turn this one full turn, which then wants to pull these together such that it moves down by one thread pitch. And it tells you the pitch of the thread is 1.5 millimeters. Okay? So it means this thing wants to pull these together 1.5 millimeters. Now, unfortunately, it's loaded. So that pulls this thread closer to this, but that causes these two rods to stretch. This is this region, and then obviously also these two rods to stretch. Okay? So that's the problem we want to solve. Okay? They want to find the forces in the rods, I'm assuming. Determine the forces in the rods. Okay. All right. So let me draw the picture a little better. My office is a mess. Good thing you can't see how messy my office is today. So this is problem 440. Here's the little detail. Here's the upper portion. So this is point B. This is point D. This distance, well, I'll give it down to here. This distance down to here is given as, because that's where the length of the rod is, 0.75 meters, okay, because this actually goes through. So that's the length of rod. AB, which is the same initially as the length of the rod, CD, and then we've got here point E, come down. Here's the turnbuckle detail, right? So that's the detail I'm trying to show there, and comes down again and is pinned at point F. And this distance here is also 750 millimeters, or 0.75 meters. And these distances here they give, well, we don't really need them. They're equal, and they are 1/2 of a meter. These guys have, they're all the same. They have a cross-sectional area of 125 square millimeters, and they're made out of steel, so Young's modulus is 200 GPa. This is rigid, all right? Okay, so the first question that always is going to kind of pop up in these things is, is this allowed to rotate? And in practice, right, it's arguable about whether it would rotate. You'd have to actually look at some of the details of the design, all right? In this problem, there's two reasons why you'd say it doesn't rotate. One is, if you look back at the example problems in the book, the ones they solve have no rotation. Okay, that's kind of a cop-out. But the other one you can look at to justify why there would be no rotation is this is completely symmetric on the top. So basically, if I look down this line, I have a line of symmetry. All right? So there's nothing that would cause it to kick this way or that way. The loading is symmetric, or the mechanism that loads it up, the turnbuckle is right down the center line. These guys are identical, same length, same stiffness. So, if this had a different length, or if this had a different length, then you would have some asymmetry that might cause it to kick around. But in this case, we're going to assume no. Okay? So it's rigid. It does not rotate. Okay, so if we look at the free body diagram, if you will, we have, well, let's do the free body diagram of this bar, right? We have the force in element EF, so let's call that reaction, let's call it P. P in EF, that's the force in this element. Then we have the force in CD, and also the force in AB. Okay? And since it doesn't rotate, the only equation we can write from an equilibrium standpoint is sum of forces in the y direction go to 0, or FAB plus FCD equals, I'm calling it F, I should call it P, equals PEF. So I did the sense so that the assumed intention, and that's the sum of forces. But we have three unknowns and only one equilibrium equation. So that means we need two displacement conditions, two compatibility equations. Now what can we do here? All right. Well, one of them is easy, all right? One we can get from the fact that it doesn't rotate. And if we consider the fact that it doesn't rotate, then that tells me that the elongation of this element has to equal the elongation of this element. That's obvious just, again, from symmetry cases. You can actually even infer that these guys are the same. So delta AB has to equal delta CD. They have to be equal. All right, that's one. So this is one equation. We can call this equation 2, although I'll probably not use it. You'll see why in a second. And we need a third one, right, to solve for the 1, 2, 3 unknowns. So the third one obviously is going to have something to do with the turnbuckle, okay? So what's going to happen here? Let me try to draw this relatively neatly. So if AB increases, if delta AB is positive, then this line will move down to here. Okay? Let me try to draw this right on top of this thing. That would be delta AB. It would move that down. Okay? Now, forgetting the turnbuckle, that would mean that element EF would compress by that same amount. Okay? So you have delta AB minus delta EF, right, would equal 0. Forget about the turnbuckle, right? Forget about the turnbuckle now. So it's saying if somehow I put some loading on here, maybe it's the weight of this. We ignored the weight, right? It sags down. This one, it stretches by delta AB, which equals delta CD. That is to equal, I'm sorry. So that one plus the elongation of EF has to equal 0, okay? So we infer that this is probably going to be a negative elongation, right? Well, in this situation, right, we have the turnbuckle. So actually what happens is this distance here is not going to be 0. It actually has to become the amount of change in the turnbuckle. Okay, that's what I'm saying. So forget there's a turnbuckle. Imagine instead of a turnbuckle, there was somebody just pulling this down a little bit, right? So here's the delta AB. That moves point E down here, and then you add on to it delta EF, how much that elongates. Then this is the total elongation. Okay, that's the total elongation. All right. So if you imagine like pulling this down at this point, right, that would be the amount that this would stretch. Okay. Now in this problem, you're not actually doing that, but what happens is this amount that the whole system has to elongate is the amount that's picked up in the turnbuckle, right? That's the how close these two have to come together. That's the delta in the turnbuckle, okay? So actually what happens is this doesn't go to 0, but this has to equal to how much the threads come together in the turnbuckle, all right? So it's the turnbuckle that's, in a sense, pulling this down. So that's the second compatibility equation. I hope I explained that well. It's a little difficult to draw, but so the elongation of AB plus the elongation of EF equals the elongation of the turnbuckle, or the delta change at the turnbuckle. This is the two threads coming together. So if you can see, if there was no turnbuckle, this would go to 0, right? And then you can see here you get this the regular compatibility. Whatever this moves down, whatever AB increases in length, EF has to decrease, or vice versa, right? Whatever EF increases by, AB has to decrease by. Okay? So this is the third compatibility equation. Now, how do you get the delta in the turnbuckle? Well, that's easy. That's given just by the thread pitch of the turnbuckle. So it tells you that the thread pitch, or the lead pitch, is 1.5 millimeters. So that means if you look at the thread, right, each thread comes down. In one turn, it'll drop down 1.5 millimeters. So this is 1.5 millimeters. You turn it once, that means the total elongation of the system has to change by 1.5 millimeters. If you do it twice, it would be 3. If you turn it the other way, you'd actually be kind of having to compress them, so this would be a negative number, okay? All right. So those are the 3 equations. Let me just pause here, and I'll pick this up in a second. All right. So we had the 2 compatibility equations, and then the one sum of force equations. So that gives me 3 equations for the 3 unknowns. All right. All right. This one's actually pretty easy. You could formally write all these out in terms of the elongations of the elements, and that would be fine. But let me do, I could put PL on AE for all these terms in these 2 equations, get equation 2 and equation 3 completely in terms of the 3 unknown internal reaction forces, and then just solve that system of 3 equations for 3 unknowns. But this one's kind of an interesting one. This one allows me to kind of easily knock out one of the unknowns. So if the elongation of A and B is the same as the elongation of CD, and they're made of the same material, now that means obviously the force in the 2 have to be equal. So this one is implying that the force in AB equals the force in CD. So now, what have I done? Well, let's kind of throw this out, and now I have 2 unknowns. So we'll recast this. So now the first equation, equation 1, now becomes 2 times PAB equals PEF. And then equation 3 now becomes delta AB plus delta EF equals 1.5 millimeters. Okay? So those are the 2 equations I'm going to use. Okay, so I've kind of eliminated 1 equation. All right? Okay. Let me mention out something else as well. In this situation, it's always good to assume your internal reaction forces, well, I shouldn't say that. It's really essential in this problem to assume that your internal reaction forces are all positive. And like I always say, you should always assume that the reaction forces internally are positive in tension, all right? Or we talk about bending and torsion, positive in those sense. Why? Because the correct value of P will give me a delta that's positive when it elongates. Now obviously here, these guys are going to be probably of a different sign. I think. Well, no, maybe not. No, actually they'll be the same sign. But, since you're solving for these coupled systems, you need to have the same sense on P as you do on the deltas. So in other words, if you just always assume that delta being positive means elongation, and that the internal reaction force is positive in tension, then you'll always be consistent. And I think that makes sense. If you start flipping them around, then you certainly can do it, but you just have to be very careful about the signs. And it's usually very difficult to do something like that, especially on something like an exam. Okay, so I always recommend that. Assume positive elongations. Elongations are positive values of delta, and assume that internal reaction forces are positive in tension. So that's why I drew these forces this way, and you can see that affected my sum of forces balance. All right. Well, that's the hard part of the problem. The rest of it's relatively easy. So let's finish off the rest of it here. Okay? So here are 2 equations. Let's start writing those. So delta AB is the force in AB times its length, which is the 0.75 meters, over its cross-sectional area, which is 125 times 10, 0.125 times 10 to the minus third meters squared, okay, times G, which is 200 times 10 to the ninth pascals, okay? Likewise, we can get the elongation in EF. It's the force in EF times its length, which is also 0.75 meters. Same stuff, 0.125 times 10 to the minus third meters squared, 200 times 10 to the ninth pascals, okay? So now I have 2 PAB minus PEF equals 0, and then from this you can actually see that both these guys get multiplied by the same term. So I got 0.75 meters over 0.125 times 10 to the minus third meters squared, 200 times 10 to the ninth pascals, times PAB plus PEF equals 1.5 millimeters. So let's 1.5 times 10 to the minus third meters. Okay, so now everything's all in SI units. All right. Okay, so we can do a simple substitution. Let's just put into PEF 2PAB, okay? And then this term here becomes 3PAB. Then we can directly solve for PAB. So PAB is going to be 1/3 of the, we're going to divide by that, multiply by the reciprocal, 0.125 times 10 to the minus third meters squared, 200 times 10 to the ninth pascals, 0.75 meters times the 1.5 times 10 to the minus third meters, okay? So the meters will cancel out, meters squared will cancel out with the Newton meter squared to the pascal and be left just with pascals, okay? So when I do that, on the calculator, that becomes 125. Okay, this becomes PAB is actually equal to 16.7 kilonewtons, okay? And we know that's also going to be the force in CD. Now the force in EF, we can get from that. It's going to be equal to 1/2 the force in AB. And so that is just 8.35 kilonewtons. Okay?